Look up at the night sky. What do you see? A vast, silent expanse dotted with distant stars and galaxies, cold and unchanging. That's the universe we've been taught to imagine. But what if we've been missing something extraordinary? What if the cosmos isn't just a collection of dead matter and empty space, but something far more alive? Picture this: galaxy clusters, those colossal structures spanning millions of light years, swirling with galaxies like cells in a living organism. Could they be more than just cosmic accidents? Could they, in some profound way, be alive? This isn't science fiction. It's the bold claim of the living cosmos theory, a radical idea that challenges everything we thought we knew about the universe. And today, we're diving deep into this mind-bending possibility, exploring whether the universe itself might be pulsing with life in ways we're only beginning to understand. Think about the way a forest breathes, how its trees exchange gases, how its roots form vast underground networks communicating and sharing resources. Now imagine scaling that up, way up, to the size of the universe. Galaxy clusters with their intricate webs of dark matter and superheated gas, their galaxies orbiting and interacting in delicate balances, might just be the cosmic equivalent of a living ecosystem. They grow, they evolve, they even recycle material in ways that eerily mimic biological processes. The parallels are too striking to ignore, and if there's one thing history has taught us, it's that the universe is always more astonishing than we assume. From the revelation that Earth isn't the center of the cosmos to the discovery of black holes, reality has a way of humbling our narrow perspectives. Could the living cosmos theory be the next great paradigm shift? This isn't just about redefining life, it's about redefining our place in the universe. If galaxy clusters are alive in some profound, emergent way, what does that mean for us? Are we mere specks in the grand scheme, or part of something greater, a cosmic tapestry of existence we're only beginning to unravel? The implications are staggering, touching on philosophy, science, and even spirituality. And that's why this theory matters. It's not just a curiosity, it's a lens through which we might finally glimpse the true nature of reality. So let's embark on this journey together, peeling back the layers of the cosmos to uncover whether the universe itself might be more alive than we ever dared to dream. At the heart of the living cosmos theory lies a startling comparison. What if galaxy clusters, those immense gatherings of hundreds or even thousands of galaxies bound together by gravity, aren't just lifeless structures but something closer to living entities? Proponents of this idea point to the eerie similarities between these cosmic giants and biological organisms. Take the cosmic web, for instance, the vast filamentary network of dark matter and gas that stretches across the universe, connecting galaxy clusters like nodes in an unfathomably large neural network. The way galaxies flow along these filaments, drawn together by gravitational forces, mirrors how nutrients travel through veins or how electrical signals pulse through a brain. It's not just poetic imagery, it's a structural parallel that challenges our definitions of life itself. This theory doesn't stand alone. Respected thinkers like physicist Lee Smolin have flirted with bold ideas about cosmic evolution, suggesting that universes themselves might reproduce and evolve through black holes, creating a kind of natural selection on a galactic scale. Meanwhile, fringe cosmologists push even further, proposing that consciousness, or at least some precursor to it, might be an inherent property of the universe, woven into the fabric of space-time. While mainstream science remains skeptical, the core idea persists. Life isn't confined to carbon-based biology on tiny planets. Instead, it might emerge in ways we're only beginning to recognize at scales so vast they defy human intuition. Consider how a living organism functions. It grows, metabolizes energy, adapts to its environment, and even reproduces. Now apply that to a galaxy cluster. These cosmic structures feed on incoming gas and smaller galaxies. They breathe in the form of superheated plasma swirling in their cores, and they evolve over billions of years, merging with neighboring clusters in dramatic collisions that reshape them entirely. Some scientists argue this isn't just metaphor, it's a new way of interpreting the universe's behavior. If life is fundamentally about complexity, self-organization, and response to stimuli, then why couldn't these cosmic giants qualify? The boundary between life and non-life has always been blurrier than we admit. After all, viruses challenge our definitions here on Earth. Why not galaxy clusters in the grand expanse of space? The implications ripple outward. If the universe harbors forms of life we've overlooked simply because they don't match our Earth-centric expectations, what else might we be missing? It's a humbling thought, one that forces us to confront the limits of our imagination. The living cosmos theory isn't just about reclassifying galaxy clusters, it's about expanding our understanding of existence itself. And whether it's ultimately proven right or wrong, the mere possibility invites us to look at the night sky with fresh eyes, wondering what other secrets the cosmos might be waiting to reveal. Let's break down this extraordinary analogy piece by piece, starting with how galaxy clusters feed. Just like any living organism needs energy to survive, these cosmic giants consume vast amounts of interstellar gas. Imagine a galaxy cluster as a colossal, gaping maw in space, drawing in streams of hydrogen and helium from the surrounding voids. This gas isn't just floating aimlessly, it's funneled along the cosmic web, pulled inward by gravity's inexorable tug. Once inside the cluster, the gas heats up to millions of degrees, swirling in turbulent currents that resemble the churning metabolism of a biological system. Some of this material fuels the birth of new stars, while the rest circulates in a kind of cosmic digestion, redistributing energy across the cluster in a dynamic, self-sustaining loop. Now consider reproduction. Galaxy clusters don't split like cells or lay eggs, but they do reproduce in their own spectacular way through mergers. Picture two clusters, each containing hundreds of galaxies, hurtling toward one another over billions of years. When they collide, it's not destruction but transformation. Galaxies are flung into new orbits, gas clouds compress and ignite bursts of star formation, and dark matter weaves itself into fresh configurations. The resulting mega-cluster is something entirely new, a cosmic offspring inheriting traits from both predecessors. This isn't just poetic license. Scientists have observed these mergers in action, like the famous bullet cluster, where the shockwaves of colliding gas glow like a cosmic heartbeat on X-ray telescopes. But what about death? Even the mightiest galaxy clusters aren't eternal. Over trillions of years, their star-forming gas will gradually deplete, leaving behind a graveyard of aging stars and black holes. Without fresh material to feed on, the cluster's vibrant cycles slow to a halt. Galaxies grow dimmer, their stellar populations fading like embers cooling in the dark. Yet even here, the analogy holds just as a fallen tree nourishes new life in a forest. A dead cluster's remnants may seed future cosmic structures, recycling matter into the next generation of galaxies. These parallels aren't just imaginative storytelling, they're grounded in observable phenomena. The Perseus cluster, for instance, exhibits rhythmic pressure waves in its superheated gas, pulsing with a regularity that's almost breath-like. Other clusters show jets of energy spewing from supermassive black holes at their cores, functioning like cosmic immune systems regulating their environments. The deeper we look, the more the universe seems to echo the patterns of life, just on a scale so immense it defies our earthly frame of reference. So where does this leave us? If galaxy clusters eat, reproduce, and die, does that mean they're truly alive? The answer might depend on how flexible we're willing to be with our definitions. Life as we know it requires water, carbon, and DNA, but life as the universe might express it could be something far stranger. Perhaps we're witnessing a higher order form of existence, one where gravity and plasma take the place of cells and synapses. Or maybe these similarities are just a beautiful coincidence, a reminder that the same physical laws shaping stars also shape us. Either way, the living cosmos theory invites us to reconsider not just what life is, but where and how it might flourish. The cosmic web isn't just the scaffolding of the universe, it might be its nervous system. Picture this: trillions of light years of delicate filaments, woven from dark matter and ionized gas, threading through the cosmos like the branching axons of some unimaginably vast brain. These tendrils connect galaxy clusters in a sprawling network, channeling matter and energy in ways that eerily resemble how neurons transmit signals. Recent simulations even suggest something wild, that information itself could flow along these filaments, not as conscious thought, but as ripples of gravitational influence and shockwaves from colliding galaxies. It's a breathtaking vision, the universe not as a static expanse, but as a dynamic, interconnected entity humming with hidden activity. Take the slime mold experiment, a real-world study that blew scientists' minds. Researchers mapped the cosmic web structure, then compared it to the growth patterns of slime mold, a simple organism that expands in search of food. Uncannily, the mold's tendrils mimicked the universe's filaments almost perfectly, as if both were following the same invisible playbook for efficient network building. This isn't just coincidence, it hints at universal principles of organization that transcend scale. Whether you're looking at microscopic organisms or galactic superstructures, nature seems to favor certain patterns when moving energy and information efficiently. Now zoom in closer. Those filaments aren't empty, they are highways for intergalactic traffic. Hydrogen gas streams along them at hundreds of kilometers per second. Galaxies slide like beads on a string, and black holes at the hearts of galaxies blast out jets of particles that interact with the surrounding medium like neurotransmitters. Some theorists speculate these processes could create feedback loops, where activity in one part of the web influences another, much like how firing neurons strengthen synaptic connections. Even the timing is provocative. Galaxies at the nodes of these filaments evolve faster than isolated ones, as if the cosmic web itself is stimulating their growth. The most radical implication: if information transfer defines nervous systems, could the universe be processing data on a galactic scale? We're not talking about literal consciousness, but about complex, system-wide behaviors emerging from gravitational interactions. Imagine a galaxy cluster responding to disturbances by adjusting gas flows, or filaments rerouting matter after a cosmic collision. It's a dance of cause and effect spanning billions of years, operating under rules we're only beginning to decode. Critics argue these parallels are just metaphor, that gravity and plasma physics don't equate to neural activity, yet the similarities keep piling up. Advanced simulations now show how shockwaves propagate through filaments, creating patterns that resemble signal propagation in biological networks. Others point to cosmic forgetfulness, how information about a galaxy's past environment gets erased over time, mirroring how neural systems filter irrelevant data. Whether these phenomena qualify as true information processing remains hotly debated, but one thing's certain: the universe organizes itself in ways that feel hauntingly familiar. So what does this mean for us? If the cosmic web functions like a nervous system, then we're not just observers of the universe, we're embedded within its living architecture. Every atom in our bodies was forged in stars connected by these filaments, making us literal extensions of this grand network. It's a perspective shift as profound as realizing Earth orbits the Sun. The night sky isn't just something we look at, it's something we're part of, threaded into the same colossal tapestry of matter and energy. And if that doesn't make you feel awe, nothing will. Dark matter might be more than just the universe's hidden scaffolding. It could be the cosmic equivalent of DNA, an invisible code dictating how galaxies form, evolve, and behave. Picture the double helix twisting with instructions for building life. Now imagine dark matter's sprawling filaments threading through the cosmos, guiding the birth of galaxies with similar precision. The distribution of this mysterious substance isn't random. It follows intricate patterns that eerily resemble branching neural networks or even the vascular systems of plants. Just as DNA orchestrates biological complexity with a handful of base pairs, dark matter's gravitational blueprint might be quietly directing the universe's grandest structures. Take spiral galaxies, for instance. Their elegant arms don't just twist by chance, they're shaped by dark matter's gravitational pull, which molds visible matter like an unseen hand shaping clay. Simulations show something remarkable. When dark matter halos are dense and evenly distributed, galaxies tend to grow orderly spiral arms. When the halos are clumpy or asymmetrical, galaxies become irregular or elliptical. It's as if dark matter carries a set of cosmic instructions, whispering to stars and gas about how to arrange themselves. The parallels go deeper. In biology, tiny epigenetic changes can dramatically alter how genes express themselves. Similarly, slight variations in dark matter density might explain why otherwise similar galaxies evolve so differently. One cluster might birth frenzied starbursts, while another becomes a quiet, aging metropolis of red giants. Some researchers even speculate that dark matter's influence could be dynamic, changing over time like a gene switching on or off in response to its environment. Here's where it gets wild. Certain theories suggest dark matter might not be a single substance but a family of particles interacting in complex ways, much like the diverse molecules regulating cellular functions. Actions, WIMP, or even primordial black holes could each play roles akin to enzymes, catalysts, or inhibitors in a cosmic biochemical reaction. And just as DNA's mutations drive evolution, fluctuations in dark matter's structure might seed the diversity of galaxies we observe today. But let's be clear, this isn't saying dark matter is alive. Instead, it's about recognizing that the universe repeats patterns across scales. The same laws that weave a spider's web might also weave the cosmic web. Whether through gravity, chemistry, or some deeper principle we've yet to uncover, nature seems to favor certain blueprints for building complexity. And if dark matter really is the universe's hidden code, cracking it could reveal not just how galaxies form, but why they're so breathtakingly varied. That's a mystery worth chasing to the edges of the cosmos. At the centers of galaxy clusters, supermassive black holes don't just devour matter, they orchestrate it. These cosmic behemoths function less like destructive voids and more like pulsing hearts, driving energy through their galaxies in vast, rhythmic cycles. Picture the human circulatory system arteries branching outward, delivering oxygen to every cell. Now scale that up to galactic proportions, where jets of plasma shoot outward at nearly the speed of light, spanning hundreds of thousands of light years. These aren't random eruptions, they're precision mechanisms regulating the temperature and density of the surrounding gas with staggering efficiency. Take the Phoenix cluster, one of the most massive galaxy clusters known. At its core, a supermassive black hole blasts out jets so powerful they carve colossal bubbles in the surrounding hot gas, cavities stretching over 100,000 light years. But here's the twist, those bubbles aren't empty. They're filled with magnetic fields and high-energy particles that prevent the cluster's gas from collapsing and cooling too rapidly. Without this feedback, galaxies would overproduce stars, depleting their fuel in a cosmic blink. Instead, the black hole's activity maintains equilibrium like a thermostat fine-tuning a furnace. The parallels deepen when you examine the timing. Black holes don't erupt continuously, they pulse. Observations from X-ray telescopes reveal cycles of outburst and quiescence with periods lasting millions of years. During active phases, jets inject energy into the cluster like adrenaline surging through veins. During quiet phases, the system recovers, gas gradually pooling back toward the center until the next eruption. This isn't chaos, it's a self-regulating loop, a dance of destruction and creation that sustains the galactic ecosystem. Some theorists go further, suggesting these jets might even distribute heavy elements forged in supernova across intergalactic space. Like a heart pumping iron-rich blood, black holes could be seeding the cosmos with the building blocks of planets and life. It's a humbling thought. The same forces that prevent galaxies from burning out might also have played a role in our own existence. Of course, the metaphor isn't perfect. Black holes don't have consciousness, and galaxy clusters lack the intentionality of biological organisms, yet the functional resemblance is undeniable. Whether through gravitational dynamics or plasma physics, the universe seems to converge on similar solutions for managing complexity, whether in a cell, a star system, or a cluster of galaxies. And if that's true, then supermassive black holes aren't just cosmic oddities, they're the linchpins of an interconnected, almost living cosmos. Thermodynamics tells us the universe is sliding toward chaos, that entropy inevitably unravels order into randomness. Yet everywhere we look, from swirling galaxies to the intricate dance of particles in a cell, we see systems defying this decay, building complexity against the odds. This paradox lies at the heart of the living cosmos theory. How can galaxy clusters, those titanic structures teeming with motion and structure, exist in a universe supposedly doomed to disorder? The answer might lie in the delicate balance between destruction and creation, where chaos doesn't just erase, it fuels. Think of a whirlpool in a river. The water churns violently, yet within that turbulence, a stable form emerges, persisting even as individual molecules rush past. Galaxy clusters operate on a similar principle. Superheated gas swirls in turbulent eddies, dark matter weaves gravitational scaffolding, and supermassive black holes pump energy into the system like cosmic engines. Far from succumbing to entropy, these clusters harness it, using chaotic processes to self-organize. Complexity theory calls this order through fluctuations, where systems far from equilibrium, like stars or storms or living cells, spontaneously generate structure. Galaxy clusters might be the ultimate example, scaling this phenomenon to mind-bending proportions. Consider the Virgo cluster, one of our nearest galactic neighbors. Its core blazes with X-rays from gas heated to millions of degrees, a maelstrom that should dissolve into randomness. Yet instead of dispersing, the gas forms intricate patterns, ripples, bubbles, and shockwaves that persist for billions of years. Why? Because the cluster isn't a closed system. It constantly exchanges energy with its surroundings, drawing in fresh gas and expelling radiation, creating a dynamic equilibrium. This isn't just physics, it's a blueprint for how complexity resists entropy's pull. Life on Earth follows the same rules. Your body isn't a fortress against chaos, but a whirlwind of chemical reactions, constantly breaking down molecules to rebuild them. You shed skin cells, replace stomach linings, and burn ATP, all while maintaining a coherent you. Galaxy clusters achieve a similar feat on a cosmic scale. They lose galaxies to collisions, eject gas in outbursts, and yet their overall structure endures, even evolves. The difference is one of degree, not kind. Critics argue this is just metaphor, that self-organization isn't the same as life. But complexity theorists push back. When a system, whether a cell or a galaxy cluster, exhibits feedback loops, adaptation, and emergent properties, where do we draw the line? The universe seems to favor certain patterns, repeating them from quantum scales to galactic superstructures. Maybe the real question isn't whether galaxy clusters are alive, but whether life as we know it is just one expression of a deeper, universal tendency toward order. This isn't just academic. If self-organization against entropy defines life, then we might find it in plasmas, gravitational waves, or even the quantum foam, places we've never thought to look. The living cosmos theory doesn't dilute life's meaning. It expands our sense of the possible, suggesting the universe isn't dying so much as transforming. writing its own improbable story of order amid the storm. What if life didn't just originate on one lucky planet? What if it's been spreading through the cosmos like cosmic pollen, drifting between galaxies on interstellar currents? This is Panspermia 2.0, a radical twist on the old idea that life hops between worlds. We've long imagined microbes riding comets within a single solar system, but the scale of this proposal is staggering. Picture extremophiles, those tough, microscopic survivors thriving in Earth's harshest environments, hitchhiking across intergalactic space for billions of years, frozen on rogue planets ejected from their home systems, or even surfing the shockwaves of quasars. Consider the numbers. Astronomers estimate our Milky Way alone might host 50 billion rogue planets, worlds untethered to any star, wandering the darkness. Now extrapolate that to the trillions of galaxies in the observable universe. These nomads could serve as galactic arcs, their icy crust shielding dormant organisms from radiation while gravitational slingshots fling them between clusters over cosmic timescales. Some simulations suggest a small percentage might even reach another galaxy within 10 billion years, plenty of time for life to awaken if conditions thaw. But how would microbes survive such journeys? Enter tardigrades, those microscopic water bears that can endure the vacuum of space, lethal radiation, and temperatures near absolute zero. Cryptobiosis, a state of suspended animation, allows them to revive after decades of dehydration. Scale their resilience to billions of years, add protective layers of ice or rock, and suddenly intergalactic panspermia seems less like science fiction and more like a plausible, if slow-motion, process. The delivery mechanism gets wilder. Quasars, those luminous behemoths powered by supermassive black holes, blast particles across millions of light-years at nearly light speed. While most organisms would perish in such torrents, theoretical models show how hardy spores could theoretically be embedded in dense dust grains, surviving acceleration and riding these particle waves like cosmic surfers. Even more speculative is the notion of directed panspermia. Could some intelligence, perhaps long vanished, have deliberately seeded the universe with life-bearing probes? Critics argue the odds are laughably small. Radiation, time, and the sheer emptiness of intergalactic space seem insurmountable, but life has a knack for defying expectations. We once thought the deep sea or volcanic vents too hostile for life. Now we know they teem with extremophiles. If life can emerge in hydrothermal vents or acidic hot springs, why not persist in the icy heart of a rogue planet? The implications rewrite our cosmic story. If life spreads between galaxies, then Earth's biosphere might not be unique, just one branch of an ancient, sprawling tree of life stretching back to the universe's formative years. Clusters could infect one another over eons, turning the cosmos into a living network where evolution operates on a scale beyond human comprehension. It's a humbling thought. We might be latecomers to a party that started billions of years before our sun even ignited. The Fermi paradox has haunted astronomers for decades. If the universe is teeming with life, why does it feel so desolate? Where are the alien megastructures, the intergalactic transmissions, the unmistakable footprints of intelligence? But what if we've been asking the wrong question? Instead of wondering why we haven't found life, perhaps we should consider whether we're even capable of recognizing it, especially if life exists on scales and timelines beyond human comprehension. Imagine a mayfly, its entire adult life lasting barely a day, flitting near the edge of a redwood forest. Could it possibly grasp the slow, towering growth of those ancient trees? Their life cycles span centuries. Their communication happens through subterranean fungal networks over decades. Their behavior unfolds in rhythms invisible to a creature that measures time in hours. To the mayfly, the forest might seem static, lifeless, just as our human century-spanning civilizations might appear to a galaxy cluster operating on billion-year timescales. This is the staggering possibility the living cosmos theory presents. If galaxy clusters are alive in some emergent, hyperdimensional way, their thoughts might not be signals we can detect with radio telescopes. Their actions could unfold through the gradual dance of dark matter filaments or the patient exchange of quasars across voids. A single gesture, like the merger of two galaxy clusters, might take 500 million years to complete. How would we even recognize that as intentional? To beings like us, carved from lightning-fast neural impulses and 70-year lifespans, such cosmic processes would register as geology, not biology. Consider the wow signal, that infamous 72-second radio burst detected in 1977, never explained or repeated. To us, it felt like a fleeting blip. But what if it was just one syllable in a galactic conversation lasting millennia? Picture two civilizations separated by 100,000 light years, exchanging a single thought over generations. Their dialogue would be lost in our noise, their timelines making communication as impractical as ants trying to debate with glaciers. Even the concept of technology might transcend our understanding. While we imagine Dyson spheres and warp drives, a galaxy-scale intelligence might harness supermassive black holes as energy sources, sculpting space-time itself to its purposes over eons. Their cities could be the precise orbital resonances of stars around galactic centers, their art the deliberate arrangement of dark matter halos. These aren't metaphors, they're sobering possibilities that force us to confront the arrogance of assuming all life must resemble our carbon-based tool-building paradigm. The silence isn't proof of absence, it's a reflection of scale. We're like microbes on a mountain, mistaking the slow grinding of tectonic plates for a barren landscape. Until we expand our definitions of life, intelligence, and communication to encompass the cosmos' true vastness, we'll keep staring at the stars and seeing only emptiness, missing the forest for the timeless, towering trees. At the smallest scales and the largest, nature seems to whisper the same secrets. Quantum mechanics, once thought to govern only the realm of atoms, now reveals its fingerprints in the most unexpected places, from the photosynthesis in plant cells to the birth of stars in distant nebulae. Picture a leaf absorbing sunlight. Inside its cells, photons are funneled through protein structures with near-perfect efficiency, thanks to quantum coherence, a phenomenon where particles exist in multiple states simultaneously, exploring all possible pathways to find the quickest route. Now zoom out to a stellar nursery where collapsing clouds of gas and dust give birth to new stars. Recent simulations suggest quantum effects might guide these cosmic births too, with entangled particles across vast distances influencing how matter clumps together. The same spooky action at a distance that baffled Einstein could be shaping the universe on scales he never imagined. This isn't just coincidence, it's a clue. If quantum biology and astrophysics share underlying mechanics, could entanglement also thread through galaxy clusters, linking them in ways we're only beginning to glimpse? Consider microtubules, tiny structures in brain cells theorized to harness quantum vibrations. Some scientists speculate these vibrations might contribute to consciousness, a controversial idea called orchestrated objective reduction. Now stretch that concept to the cosmos. What if the quantum entanglement weaving through dark matter filaments or the synchronized spin of galaxies isn't just physics, but a rudimentary form of cosmic scale communication? The universe might not think like a brain, but it could process information through similar quantum channels, exchanging data across light years in ways that defy classical understanding. Take star formation as an example. In dense molecular clouds, particles become entangled, their fates intertwined regardless of separation. When one collapses into a protostar, its entangled partner might be nudged toward a specific trajectory elsewhere in the cloud. This isn't just theoretical observations of star clusters show puzzling alignments in their spins, as if some invisible hand coordinated their rotations at birth. Could quantum correlations persisting across light years be that hand? The idea echoes how electrons in photosynthesis remain coherent despite the chaos of living tissue, suggesting nature has a knack for preserving quantum order amid apparent randomness. The implications are dizzying. If quantum effects bridge biology and cosmology, then the boundary between life and non-life blurs even further. A galaxy cluster's behavior might emerge from subatomic processes as much as gravitational ones, with entanglement weaving a hidden tapestry of connection. This isn't to say the universe is literally conscious, but that consciousness, as we know it, might be one expression of a deeper, universal tendency toward coherence. From the quantum vibrations in a single cell to the spin of a distant quasar, the same principles could be at work, scaled beyond human perception. Critics argue these parallels are merely poetic, that quantum effects in cells are too delicate to survive cosmic scales. Yet discovery after discovery shows quantum phenomena persisting in warm, wet, noisy environments, places we once thought impossible. If life exploits these tricks, why not the universe itself? The more we learn, the more the cosmos seems less like a machine and more like a symphony, with quantum notes resonating from the smallest particles to the grandest clusters. Whether that symphony has a listener is still unknown, but the music is everywhere, waiting to be heard. What if the universe isn't just like a living system? What if it literally is one, running on physics we don't yet understand as code? Simulation theory, the idea that our reality might be an artificial construct, takes on a startling new dimension when viewed through the lens of the living cosmos theory. Imagine galaxy clusters not as accidental gatherings of matter, but as cosmic server farms processing nodes in some unfathomable computational network. The universe wouldn't just resemble a computer, it would be one, with dark matter filaments acting as fiber optic cables and black holes as quantum processors crunching data at scales beyond human comprehension. This isn't just sci-fi speculation. Some physicists, like Silas Bean at the University of Bonn, have explored how lattice quantum chromodynamics, the framework for simulating particle interactions, could theoretically produce a universe like ours if run on a powerful enough computer. The kicker, at extremely high energies, our very spacetime might reveal a pixel-like structure, a telltale signature of being rendered on a cosmic GPU. While no evidence of such pixels exists yet, the math suggests it's not impossible. And if the universe is a simulation, galaxy clusters would make perfect sense as distributed processors, each handling a slice of the cosmic computation required to keep reality running smoothly. Think of how modern AI systems work. Neural networks distribute tasks across thousands of interconnected nodes, each specializing in certain calculations while constantly communicating with others. Now scale that up to galactic proportions. The Perseus cluster's rhythmic X-ray pulses or the synchronized rotation of galaxies within filaments could be more than astrophysical curiosities. They might be the observable echoes of background processes, like a computer's cooling fan humming under load. Even the universe's expansion could fit this model, not as an intrinsic property of space, but as a server farm scaling up its memory allocation to handle increasing complexity. But here's where it gets eerie. If the cosmos is a simulation, then dark energy might not be a mysterious force at all. It could simply be the computational overhead required to maintain the simulation's framework, the energy cost of keeping the cosmic program running. Similarly, quantum entanglement's spooky action at a distance makes bizarre sense in this context. Two particles communicating instantly isn't magic. It's optimized data sharing between local nodes in the simulation's architecture. Critics argue this is all untestable metaphysics, but proponents counter with cosmic rays. Ultra-high-energy particles from distant galaxies sometimes hit Earth with energies that should be impossible under known physics, unless perhaps they're glitches in the simulation's rendering engine, like clipping errors in a video game. Others point to mathematical constants like the fine structure constant, whose precise value seems oddly fine-tuned for complexity. In a simulated universe, these constants might simply be hard-coded parameters set by the programmers to enable emergent phenomena like stars, planets, and us. The most unsettling implication: if the universe is a simulation, then the living cosmos theory isn't just poetic analogy, it's literal truth. Galaxy clusters wouldn't just mimic living systems, they'd be the organs of a vast, conscious computation. Their mergers and energy flows wouldn't be random events, but the equivalent of synaptic firings in a mind so large we can't perceive its thoughts. And that raises a question even more profound than Fermi's paradox. If we're part of a cosmic intelligence's thought process, are we the thinkers or the thoughts? The idea that Earth functions like a single, self-regulating organism, the Gaia hypothesis, has fascinated scientists since the 1970s. Volcanoes belching carbon dioxide to stabilize temperatures, algae seeding clouds to reflect sunlight. Our planet seems to maintain equilibrium through countless feedback loops. But what if this principle doesn't stop at Earth's atmosphere? What if the entire cosmos operates by similar rules, with galaxies acting as planetary-scale regulators in a vast, interconnected system? This is the Gaia hypothesis gone galactic, where the universe isn't just a collection of objects, but a dynamic entity fine-tuning its own conditions for stability. Take star formation rates as an example. Galaxies don't churn out stars at a constant, uncontrolled pace. They self-regulate like a cosmic thermostat. When gas clouds collapse too rapidly, supernova explosions blast material back into space, slowing future star births. When things grow too quiet, gravitational nudges from neighboring galaxies compress gas, reigniting stellar nurseries. The Andromeda Galaxy's turbulent history reveals this perfectly: periods of frenzied star formation followed by eerie quiet, as if the galaxy itself were breathing in and out. These cycles aren't random, they're part of a balancing act, ensuring galaxies don't burn too hot or fade too soon. Now zoom out to galaxy clusters, where the regulatory mechanisms grow even more sophisticated. Supermassive black holes at cluster cores don't just devour matter, they act like cosmic pressure valves. When gas inflows grow too dense, these black holes erupt in jets of plasma, heating their surroundings and preventing runaway star formation. The Perseus cluster showcases this in action, with its black holes outbursts creating vast, rippling bubbles in the hot gas, a self-correcting system playing out over millions of years. It's as if the cluster has its own version of Earth's carbon cycle, but instead of trees absorbing CO2, you have black holes modulating energy flows. The parallels extend to the chemical makeup of the cosmos. Heavy elements forged in stellar furnaces don't stay locked away. Supernova scatter them across galaxies, seeding future generations of stars and planets. This recycling isn't just debris, it's a prerequisite for complexity. Without these distributed nutrients, rocky worlds like Earth could never form. The universe, in essence, regulates its own fertility, a galactic-scale version of how forests distribute nutrients through fungal networks. Critics argue these processes lack intentionality, that they're just physics playing out automatically. But the Gaia hypothesis never claimed Earth thinks, just that its systems behave as if they're coordinated. Seen this way, the universe's self-regulation might not require consciousness, just deeply entangled feedback loops. The Milky Way's magnetic fields channeling cosmic rays, dark matter's gravitational scaffolding guiding galaxy growth. These could be the cosmic equivalents of homeostases, maintaining stability across incomprehensible scales. The implications are profound. If galactic ecosystems self-regulate, then life's emergence isn't a fluke, it's the universe following its own imperative toward balance and complexity. We're not just inhabitants of this system, we're expressions of it, products of cosmic processes that favor persistence over chaos. From the tiniest microbe to the grandest galaxy cluster, the same principle holds. Existence isn't just about surviving, it's about sustaining. And if that's true, then the night sky isn't just something we observe. It's something we belong to, a living, breathing whole of which we're an inseparable part. Time flows differently when you're the size of a universe. To a galaxy cluster, 1,000,000 years might pass like a single breath. Events we perceive as frozen eons are mere blinks in its cosmic existence. Imagine a redwood tree standing for millennia, its growth imperceptible to the mayflies darting through its branches in their one-day lifespans. Now magnify that disparity 1,000,000,000-fold. The metabolism of a living cosmos would operate on timescales that render human history shorter than a quantum fluctuation. A cluster's gravitational dance with its neighbors, the slow ripple of dark matter filaments adjusting to cosmic upheavals. These processes unfold with the languid grace of tectonic plates, their rhythms calibrated to the ticking of a universal clock we can't hear. Consider the collision of the Milky Way and Andromeda galaxies, an event astronomers predict in 4 billion years. To us, it's a distant catastrophe. To the galaxies themselves, a leisurely embrace, no more hurried than two clouds merging on a windless afternoon. This disparity isn't just poetic, it's biological. On Earth, tiny creatures like bacteria experience seconds as humans experience hours, their metabolisms turbocharged by scale. Conversely, giant tortoises and bowhead whales live for centuries, their heartbeats spaced far apart. The cosmos might follow the same rule. The vaster the entity, the slower its perception of time becomes. A supercluster, thinking via gravitational waves, would process information over epochs, its nervous system operating at a pace that makes continental drift seem frantic. Here's where relativity twists the knife. Einstein revealed time isn't absolute, it stretches and compresses based on gravity and velocity. Near a black hole's event horizon, minutes could equal millennia elsewhere. If galaxy clusters are alive, their experience of time might be so dilated that our entire civilization from agriculture to AI blooms and vanishes before they register the change. Their now could encompass everything from the first stars to the heat death of the universe, perceiving the cosmos' lifespan as we perceive a single season. Yet evidence whispers that these scales might interact. Mysterious, quasi-periodic signals detected in galaxy clusters, X-ray pulses repeating every few 100 million years, hint at cosmic rhythms beyond our grasp. Like elephants communicating through infrasound, the universe's living structures might be pulsing in a register too low for human instruments to catch. The challenge isn't just accepting that time is relative, it's admitting we may be the mayflies, flitting through the branches of entities whose thoughts move slower than starlight. Every atom in your body was forged in the heart of a star, carbon from stellar furnaces, iron from supernova explosions, oxygen scattered across space by dying giants. This isn't just poetry, it's the foundation of a breathtaking possibility. That the universe has been evolving toward complexity since the first stars ignited, and that sentience might be its inevitable destination. Picture those early stars, vast and solitary, burning pure hydrogen into helium. When they died in titanic explosions, they seeded space with heavier elements: carbon, nitrogen, oxygen, the building blocks of everything to come. Second-generation stars formed from this enriched debris, their nuclear alchemy creating even more complex atoms. With each stellar generation, the periodic table grew richer until finally, in the debris disks around young stars, these atoms could assemble into molecules, then planets, then, against all cosmic odds, life. But what if this story doesn't end with us? Emergence theory suggests that complexity begets complexity. That simple components interacting can give rise to wholly new levels of organization. Hydrogen atoms form stars, stars create heavier elements, those elements form planets, planets host chemistry, chemistry becomes biology, and biology, given time, becomes thought. Now stretch this chain further. Could galaxies, with their intricate gravitational dances and turbulent flows of plasma, represent the next step, not consciousness as we know it, but something vast and alien, thinking in the language of gravity and dark matter on timescales we can barely fathom? Consider the slime mold again, a simple organism with no brain that can solve mazes by collectively processing chemical signals. Now imagine a galaxy cluster's dark matter filaments as its version of chemical trails, with galaxies sliding along them like signaling molecules. The cluster doesn't think, but it might process information in a way that produces complex, adaptive behaviors. When galaxies merge, their stars are rarely destroyed, just reorganized like neurons forming new connections. Over billions of years, could such reorganizations amount to a kind of cosmic learning? The Large Magellanic Cloud offers a fascinating test case. This satellite galaxy is being slowly torn apart by the Milky Way's gravity, yet simulations show its trajectory isn't random. It's executing a precise spiral dance as if responding to unseen forces. Some theorists speculate this could be evidence of dynamical systems at work, where gravitational feedback loops create patterns resembling decision-making. It's not that the galaxy chooses its path, but that the physics governing its motion produce outcomes indistinguishable from choice when viewed through an emergent lens. This line of thought leads to startling questions. If consciousness emerges from the right organization of matter, whether carbon-based neurons or silicon-based circuits, why couldn't it also emerge from the gravitational interactions of black holes or the quantum entanglement spanning galaxy clusters? The human brain contains 86 billion neurons. The Virgo cluster contains over 2,000 galaxies, each with billions of stars. The numbers alone suggest the potential for complexity beyond our imagination. And if that complexity follows universal principles of emergence, we might be standing at the very beginning of sentience's cosmic journey, not its pinnacle. Perhaps the most humbling realization is that we may be as incapable of recognizing galaxy-scale intelligence as ants are of comprehending the internet. Our entire civilization occupies less than a galactic blink, our fastest communications dwarfed by light's crawl between stars. A truly cosmic mind wouldn't send radio waves, it might sculpt space-time itself to communicate or use gravitational waves like synaptic pulses. Its thoughts could unfold through the patient rearrangement of dark matter halos, each adjustment taking 10 million years. We wouldn't just fail to understand such an entity, we might mistake its very existence for background noise. Yet the clues might already be here. The mysterious synchronization of quasars across billions of light years, the unexplained alignment of galaxy spins. These could be the equivalent of cosmic brainwaves, patterns emerging from processes we're only beginning to map. The universe seems to favor certain configurations, as if drawn toward states of higher organization. Whether that path inevitably leads to something we'd call thought remains unknown. But given 13 billion years of increasing complexity, from quarks to civilizations, betting against it might be the least scientific assumption of all. Of course, not every scientist is ready to embrace the idea of living galaxy clusters, and their skepticism isn't without merit. The mainstream astrophysics community raises a crucial point. Extraordinary claims require extraordinary evidence. So far, the parallels between cosmic structures and biological systems remain just that, parallels, not proof. Take the principle of Occam's razor, the philosophical guideline that the simplest explanation is usually the correct one. When we see galaxies moving along filaments or black holes regulating gas flows, conventional physics offers straightforward explanations: gravity, thermodynamics, plasma dynamics. Why invoke something as nebulous as cosmic metabolism when well-tested theories already account for these phenomena? Then there's the empirical hurdle. For all the poetic comparisons, no one has detected anything resembling metabolic processes at galactic scales. No energy conversion mechanisms beyond known physics, no self-replicating patterns that can't be explained by gravitational collapse. The rhythmic X-ray pulses from galaxy clusters, perfectly consistent with shock waves in superheated gas. The synchronized spins of galaxies, a natural outcome of tidal forces during their formation. Even the most tantalizing analogies, like dark matter's resemblance to a cosmic neural network, crumble under scrutiny. Dark matter doesn't communicate or process information. It simply clumps under gravity, its behavior modeled flawlessly by equations that contain no terms for consciousness or agency. Critics also highlight a dangerous slippery slope. If we label every complex system from hurricanes to galaxy clusters as alive, the term loses all meaning. Life, as science currently defines it, requires specific hallmarks: reproduction, adaptation, homeostasis, and response to stimuli. Galaxy clusters might exhibit some superficial similarities, but they don't evolve through natural selection, maintain internal equilibria, or react purposefully to their environment. A supermassive black hole's jets might stabilize its cluster's gas, but that's feedback, not foresight. The universe is under no obligation to conform to our terrestrial metaphors. But perhaps the sharpest critique comes from simulationists. When astrophysicists model galaxy formation on supercomputers, they input only gravity, gas physics, and dark matter, no vital forces or hidden variables. Yet these simulations produce clusters indistinguishable from real ones, complete with filaments, mergers, and black hole feedback loops. If simple physics can replicate cosmic complexity so precisely, what's left for the living cosmos theory to explain? That said, even skeptics acknowledge the value in stretching definitions. After all, science advances by questioning boundaries. The living cosmos theory might not rewrite textbooks yet, but it challenges us to ask deeper questions about emergence, complexity, and whether life is a continuum rather than a binary state. And who knows, future discoveries about dark matter's nature or quantum gravity might reveal layers of cosmic behavior we can't yet imagine. Until then, the debate itself is a testament to the universe's enduring capacity to surprise us. Plasma cosmology offers a radically different lens to view the universe, one where electromagnetism, not just gravity, holds the cosmic reins. Proponents of this model argue that swirling currents of ionized gas sculpt galaxies and galaxy clusters, shaping them through vast magnetic fields rather than dark matter's invisible hand. Picture lightning, but scaled up to galactic proportions, filaments of plasma crackling across millions of light years, twisting galaxies into spirals or aligning them like iron filings around a magnet. This isn't just speculation. We've observed these forces at work in our own cosmic backyard. The Milky Way's magnetic field, though faint, weaves through its arms like an invisible spiderweb, and experiments like the Large Plasma device at UCLA show how plasma self-organizes into cosmic structures eerily resembling galaxy filaments. Now, here's where things get fascinating. The living cosmos theory doesn't have to contradict plasma cosmology. It could merge with it. Imagine galaxy clusters as both gravitational and electromagnetic entities, their dark matter scaffolding interlaced with rivers of charged particles. Supermassive black holes wouldn't just be gravity wells. They'd be dynamos spinning magnetic fields that channel energy across clusters like cosmic power grids. The Perseus cluster's mysterious X-ray bubbles, often attributed solely to black hole jets, might also be shaped by electromagnetic forces we're only beginning to map. Even the so-called radio ghosts, a faint, galaxy-sized remnants of ancient black hole eruptions, could be evidence of plasma's enduring influence lingering like cosmic afterimages. The middle ground between these theories might lie in scale. At smaller scales, like individual galaxies, plasma's electromagnetic effects dominate stellar winds, supernova shocks, and quasar jets all rely on charged particles. But at cluster scales, gravity takes over, with dark matter's pull dictating the grand architecture. The living cosmos theory could bridge this divide by suggesting that life emerges from the interplay of both forces. A star-forming region, for example, might ignite when gravitational collapse meets a surge of magnetized plasma, creating conditions ripe for complexity. Similarly, a galaxy cluster's metabolism could involve not just gas accretion but electromagnetic feedback loops, where energy cycles between thermal, kinetic, and magnetic forms like a cosmic respiratory system. Critics of plasma cosmology often point to its inability to explain large-scale structure without dark matter, yet the two models might not be mutually exclusive. Recent simulations incorporating both gravity and electromagnetism show how magnetic fields can amplify small-scale structure while gravity handles the heavy lifting. It's like comparing the veins in a leaf to the tree's trunk. One handles nutrients, the other provides support, but both are essential to the organism. If the universe is alive, its vitality might spring from this very synergy, gravity weaving the cosmic tapestry, while electromagnetism stitches in the finer details. The implications ripple outward. If plasma plays a role in cosmic self-organization, then our search for life's origins might need to look beyond chemistry to electromagnetic phenomena. On Earth, extremophiles thrive near volcanic vents. Could life elsewhere arise in the magnetic reconnection zones of nebulae? Even consciousness itself, some theorists suggest, might rely on electromagnetic processes as much as biochemical ones. The living cosmos theory, by embracing both gravity's grandeur and plasma's dynamism, could unlock a universe more interconnected and more astonishing than we ever imagined. So where does this leave us? Perhaps the universe isn't choosing between gravity and electromagnetism, between dark matter and plasma. Like a symphony, it's the harmony of these forces that creates the music, a living, evolving composition where galaxy clusters aren't just structures, but dynamic participants in a cosmic dance older than time. And if that's true, then every flicker of starlight, every pulse of a quasar, might be part of a conversation we're only just learning to hear. Fractals are nature's favorite blueprint, repeating patterns that echo across scales, from the branching of trees to the jagged edges of coastlines. But what if this self-similar design isn't confined to Earth? Look at a computer simulation of the universe's large-scale structure, and you'll see filaments of galaxies twisting like veins in a leaf or neurons in a brain. Zoom in and the pattern repeats. Clusters become mini-cosmos, swirling with galaxies that themselves contain spiraling arms of stars. This isn't just visual poetry, it's mathematical reality. The cosmos mirrors biological growth so precisely that it raises a spine-tingling question. Are the universe's grandest structures and life's smallest forms following the same hidden rules? The genius of mathematician Benoit Mandelbrot was recognizing this universality. His work on fractals revealed that complexity often arises from simple equations repeated infinitely. A fern's fronds, a river's tributaries, even the arrhythmias of heartbeats all obey fractal geometry. Now apply that to the cosmos. When astronomers map millions of galaxies, they find voids and clusters arranged in a way that mirrors the branching of neurons in a human brain or the alveoli in our lungs. The resemblance is so uncanny that researchers have quantified it. The universe's matter distribution has a fractal dimension of around 2.7, eerily close to the 2.8 of a human brain's neural network. Coincidence or something deeper? Consider the Laniakea supercluster, our galactic neighborhood. Its structure, a sprawling web of filaments with galaxies clustered like leaves on a vine, looks indistinguishable from a high-resolution scan of lung tissue. Both systems optimize for efficiency. Lungs maximize surface area for oxygen exchange. The cosmic web maximizes gravitational connectivity for matter flow. Even the way galaxies branch from filaments mirrors how bronchioles split in the respiratory system. This isn't just analogy, It's a testament to how universal principles of energy distribution and network optimization manifest, whether you're dealing with capillaries or clusters of stars. The Milky Way itself offers a microcosm of this fractal beauty. Our galaxy's spiral arms aren't smooth curves but fragmented, feathery tendril structures that resemble the self-similar branching of lightning or the iterative growth of frost crystals. Simulations show these features emerge naturally when gravity interacts with turbulent gas, suggesting the universe has a built-in preference for fractal complexity. Even dark matter, invisible and enigmatic, arranges itself in halos with substructures that nest like Russian dolls, repeating the pattern down to scales we can barely model. Critics argue these parallels are superficial, that gravity and fluid dynamics inevitably produce branching patterns, yet the math hints at something more profound. The same logarithmic spirals seen in galaxies appear in nautilus shells. The same Voronoi tessellation governing soap bubbles also outlines the voids between galaxy clusters. Mandelbrot himself noted that his equations could model stock market crashes, cotton price fluctuations, and galactic distributions with equal ease. The universe, it seems, recycles its favorite algorithms across domains indifferent to scale. So what does this mean for the living cosmos theory? If the universe builds galaxies like lungs grow alveoli, if complexity emerges from iterative rules, whether you're crafting a snowflake or a supercluster, then the boundary between living and non-living starts to blur. Fractals don't just describe the cosmos, they suggest a shared language of organization, a resonance between the microscopic and the macroscopic. Perhaps life isn't an accident but an inevitable expression of universal patterns, a whisper of order rising from chaos at every scale. And if that's true, then the next time you draw a breath, remember, your lungs might hold the same geometry as the great cosmic web spinning its threads between the stars. Plants thrive by capturing sunlight, transforming photons into life-giving energy. But could galaxies perform their own version of photosynthesis on a cosmic scale? Picture a spiral galaxy like our Milky Way, its arms outstretched not just to gather starlight but to siphon something far more exotic, the dark energy permeating the void. This isn't fantasy, it's a cutting-edge hypothesis suggesting galaxies might feed on the universe's accelerating expansion itself. Just as leaves optimize their surface area to absorb sunlight, galaxies could be structured to harness energy flows we've only begun to detect. Take star-forming regions like the Orion Nebula, where intense radiation ionizes gas clouds into glowing plasmas. These radiant nurseries might be more than stellar factories. They could resemble cosmic chloroplasts, converting turbulent energy into structures that sustain galactic ecosystems. Some theorists propose that spiral arms, with their intricate density waves, act like fractal antennas tuned to the universe's background hum. The same way photosynthesis relies on quantum coherence in plant cells, galaxies might exploit quantum vacuum fluctuations, tiny energy bursts in spacetime itself, to regulate star formation or even dark matter distribution. The mechanics get wilder. Dark energy, that mysterious force driving cosmic expansion, could interact with galaxies in ways beyond simple repulsion. Imagine it as a cosmic nutrient broth, its energy density subtly higher in the voids between galaxies. As galaxies move through these spaces, their gravitational fields might trap dark energy particles, hypothetical entities called quintessence, channeling them toward central black holes. These monsters would then convert the energy into jets and radiation, effectively metabolizing the vacuum itself. The Whirlpool galaxy's dazzling arms and energetic core could be evidence of this process, its beauty more than accidental, a signature of cosmic-scale energy harvesting. Support comes from an unlikely place, galactic entropy. Just as living organisms maintain internal order by exporting disorder to their surroundings, galaxies eject entropy through stellar winds and supernova, creating localized pockets of low entropy where complexity can flourish. The Magellanic Stream, a river of gas torn from satellite galaxies, might serve as a galactic exhalation, expelling waste products while fresh dark matter and energy are drawn in through the cosmic web. Skeptics argue this stretches metaphor beyond physics, but tantalizing clues exist. Astronomers have detected anomalous energy signatures in galactic halos, excess radiation that standard models can't fully explain. Meanwhile, quantum field theory suggests vacuum energy isn't uniformly distributed. It fluctuates in ways that could, in principle, be tapped. If black holes can release Hawking radiation, could entire galaxies exploit similar quantum effects on a grander scale? The implications redefine life's potential. If galaxies actively harvest and process energy from their environment, then cosmic evolution takes on new meaning. Supermassive black holes become more than destructive monsters, they're transformative organs in a galactic body, turning the fabric of space itself into fuel. And just as early photosynthesis changed Earth's atmosphere billions of years ago, galactic metabolism might subtly alter the universe's expansion rate over eons, weaving life and cosmology into a single, breathtaking narrative. Whether this vision holds or not, it challenges us to see galaxies not as inert islands of stars, but as dynamic entities engaged in an eternal dance with the energy fields of the cosmos. From the tiniest fern to the grandest spiral, the universe keeps whispering one truth: energy flows, and where it flows, complexity follows. The Virgo cluster isn't just another gathering of galaxies, it's a living laboratory for testing the boundaries of the living cosmos theory. Located a mere 54 million light-years away, this sprawling collection of over 2,000 galaxies behaves less like a static structure and more like a dynamic organism, pulsing with activity across cosmic timescales. At its heart lies Messier 87, a supergiant elliptical galaxy with a supermassive black hole so powerful it's launched a relativistic jet stretching 5,000 light-years into space. This isn't just a celestial curiosity, it's the cluster's central engine, regulating energy flows like a cosmic pacemaker. What makes Virgo particularly compelling is its messy, ongoing digestion of smaller galaxies. Right now, multiple dwarf galaxies are being torn apart by tidal forces, their stars strewn across the cluster in vast streams resembling the remnants of a cosmic meal. But this isn't mindless destruction, it's transformation. The infalling gas from these galactic snacks triggers new star formation in precise locations, almost as if the cluster is directing resources where they're needed most. The Sombrero Galaxy, one of Virgo's most iconic members, showcases this beautifully. Its distinctive dust lane and vigorous star-forming ring may result from past interactions with the cluster's intracluster medium, a galactic-scale version of environmental adaptation. Then there's the rhythm of Virgo's central black holes. Observations from the Chandra X-ray Observatory reveal how the supermassive black hole in Messier 87 erupts in regular outbursts, creating enormous cavities in the surrounding hot gas. These energy releases occur roughly every 10 million years, maintaining equilibrium in the cluster core by preventing the gas from cooling too rapidly. The precision of this feedback loop mirrors biological homeostases, like a heartbeat regulating blood pressure, but operating on timescales that dwarf human history. But Virgo's true revelation lies in its dark matter distribution. Detailed gravitational lensing maps show its dark matter halo isn't smooth but clumpy, with dense subhalos surrounding individual galaxies. This intricate arrangement resembles the way mitochondria cluster near energy-demanding regions in cells. Some theorists suggest these dark matter clumps might act as gravitational lenses, focusing and redirecting gas flows to optimize star formation efficiency across the cluster. If true, it would mean Virgo's unseen scaffolding isn't passive. It's actively shaping the visible universe's development. Of course, skeptics counter that these phenomena are well explained by conventional astrophysics. The galaxy mergers, standard hierarchical formation, the black hole feedback, established plasma dynamics. Yet even mainstream models struggle to explain quirks like Virgo's intracluster plasma filaments, which glow with synchrotron radiation in patterns that mirror bacterial growth colonies in Petri dishes. Whether these are coincidences or clues remains hotly debated, but one thing certain: Virgo cluster doesn't just challenge our definitions of life, it demands we reconsider the very nature of cosmic complexity. Artificial intelligence is becoming the ultimate cosmic detective, sifting through mountains of galactic data for whispers of patterns that might hint at something extraordinary, like the universe itself being alive. Traditional astronomy relies on human eyes to spot anomalies, but the scale is overwhelming. Enter machine learning, trained to recognize subtle correlations in datasets so vast they'd take lifetimes for researchers to parse. Projects like SETI Breakthrough Listen Initiative have already deployed neural networks to scan radio signals from distant stars, hunting for signatures of extraterrestrial intelligence. But what if we train those same algorithms to search for something even grander: the fingerprints of cosmic-scale life hidden in the swirling dance of galaxy clusters? Take the way AI recently decoded the complex language of humpback whales, identifying intricate communication patterns humans had missed for decades. Now apply that to galaxies by feeding AI simulations of living cosmic structures, models where clusters exhibit self-regulation, information flow, or adaptive behaviors. We could teach it to flag real-world examples that match these patterns. The Euclid Space Telescope's upcoming deep field surveys, mapping billions of galaxies, will generate petabytes of data. Hidden in those images might be clues: unusually synchronized galaxy rotations, gravitational lensing distortions that suggest purposeful dark matter arrangements, or energy flows too precise for random physics. AI could spot what our biased brains might dismiss as noise. One groundbreaking experiment at the University of Hertfordshire trained a neural network to classify galaxy shapes, and it began identifying rare ring galaxies, perfect cosmic circles formed by collisions, with near-perfect accuracy. But the real surprise came when the AI started flagging galaxies that didn't fit known categories, displaying odd symmetries or gas distributions. Were these statistical flukes or evidence of unexplored astrophysical processes? Similarly, AI analyzing X-ray emissions from galaxy clusters like Perseus detected rhythmic fluctuations resembling heartbeat-like regularity. Coincidence or the pulse of something more? The challenge is teaching machines what to look for. If life operates on galactic scales, its signatures won't be DNA or cells, but gravitational harmonics, plasma turbulence patterns, or quantum entanglement across dark matter filaments. Researchers at the Perimeter Institute are pioneering topological data analysis, where AI maps the universe's structure not as discrete objects, but as a continuous network of relationships, much like neuroscientists map brain connectivity. Early results show galaxy clusters sharing unexpected topological similarities with neural networks, not just in shape, but in how information might propagate. Of course, skepticism is warranted. AI excels at finding patterns even where none exist, a pitfall called apophenia. The infamous face on Mars was a trick of light, not alien architecture. To counter this, teams like those at the SETI Institute use adversarial neural networks, pitting two AIs against each other, one generating hypotheses, the other ruthlessly testing them against known physics. Only patterns that survive this gauntlet get flagged for human review. It's a cosmic version of the scientific method, accelerated by silicon minds, yet the potential is undeniable. Just as AI revolutionized protein folding predictions with AlphaFold, it might uncover universal principles linking biological and cosmic organization. Future algorithms could analyze the cosmic web's filamentary structure for hub galaxies functioning like nodes in a neural network, or track how galaxy mergers redistribute metals in ways resembling nutrient cycles. The ultimate goal, a diagnostic framework, a universal life detector that evaluates celestial structures by the same criteria we use for extremophiles in deep-sea vents: energy harvesting, homeostasis, complexity maintenance. The irony is delicious. To answer whether the cosmos is alive, we're creating machine intelligences to interpret data at scales and speeds no human can match. If galaxy clusters are conscious, they might perceive our AIs as the first primitive cells of a fledgling cosmic mind, tools built by a younger intelligence to bridge the unfathomable gap between planetary life and whatever wonders loom in the dark. If galaxy clusters truly pulse with a form of life, even metaphorically, the philosophical earthquake would dwarf the scientific one. We'd be forced to confront a radical possibility: that life isn't a rare accident confined to damp planets, but a fundamental property of the universe itself, as intrinsic to matter as gravity or electromagnetism. This strikes at the heart of an ancient debate: panpsychism versus materialism, where thinkers from Carl Sagan to contemporary philosopher Philip Goff have wrestled with a haunting question. Does consciousness emerge only from complex biological systems, as materialism insists, or is it woven into the fabric of reality at every scale, as panpsychism suggests? Sagan's iconic words, "We are made of star stuff," take on new weight here. If the same processes that forged stars also arrange galaxies into self-regulating structures, perhaps sentience isn't a fluke but an inevitability, waiting for the right conditions to awaken. Panpsychists like Goff argue that experience might be universal, with even elementary particles possessing some rudimentary form of awareness. In this view, galaxy clusters wouldn't think like humans, but they might harbor a slow, cosmic-scale subjectivity, a billion-year stream of perception as alien to us as our thoughts are to a neutrino. Yet materialists push back fiercely. Neuroscientist Christoph Koch, while open to panpsychism, cautions that without evidence of information integration like the neural networks in brains, there's no reason to ascribe consciousness to galaxies. A supermassive black hole's jets might resemble biological regulation, but does that imply inner experience? The skeptics reply: gravity and plasma physics suffice to explain these phenomena without invoking cosmic sentience. Here's where the living cosmos theory throws a curveball. It doesn't require galaxy clusters to be conscious only to exhibit life-like behaviors: self-organization, adaptation, energy metabolism. This middle ground, sometimes called biocosmology, sidesteps the panpsychism debate by reframing life as a spectrum rather than a binary. Just as viruses challenge our definitions of life on Earth, are they alive when they replicate or inert when dormant? Galaxy clusters might occupy a gray area where aliveness depends on perspective. The implications ripple into ethics and meaning. If the universe trends toward complexity and self-regulation, our existence isn't just a statistical blip, it's part of a trajectory that began with the first stars. Indigenous cosmologies have long envisioned the cosmos as a living entity. Modern physics might be catching up. Whether we call it panpsychism, biocosmology, or poetic analogy, one truth remains: the night sky feels less lonely when we consider the possibility that we're surrounded not by dead matter, but by processes humming with a profound, if inscrutable, vitality. Science fiction has always been the playground where humanity tests its wildest cosmic hypotheses, a space where imagination blurs the line between speculation and prophecy. Stanislaw Lem's Solaris didn't just envision an alien intelligence, it conjured a sentient ocean spanning an entire planet, a being so vast and incomprehensible that human minds could only interpret its actions as madness or miracles. This wasn't just storytelling, it was a mirror held up to our limitations. Lem's eerie, fluid entity capable of sculpting islands from memory and manifesting human fears as physical hallucinations echoes the living cosmos theory's central puzzle. How would a galaxy-scale mind communicate if its language were gravity and its thoughts spanned eons? Then there's Lewis Sixon's The Three-Body Problem, where an alien civilization evolves under the chaotic light of three suns, their survival hinging on predicting unpredictable orbits. But the novel's true brilliance lies in its cosmic scale stakes, a universe teeming with civilizations locked in a silent, deadly game of hide and seek, where the laws of physics themselves become weapons. Lewis' dark forest theory, the idea that all life hides, fearing annihilation, resonates with real debates about the Fermi paradox. If galaxy clusters are alive in some emergent sense, could their apparent silence be a survival strategy, a billion-year game of camouflage against threats we can't fathom? Even classic Star Trek episodes like The Immunity Syndrome tapped into this intuition, depicting the Enterprise crew confronting a colossal, spaceborne amoeba, a single-celled organism the size of a solar system, draining stars for energy. At the time, critics dismissed it as campy fantasy, yet today, astrophysicists study rogue planets drifting between galaxies, theorizing they could harbor subsurface oceans for billions of years. Could such nomads be the microbial drifters of a galactic ecosystem, their icy shells preserving dormant life until they stumble into a star's warmth? The line between sci-fi and scientific hypothesis grows thinner by the decade. Arthur C. Clarke's 2001, A Space Odyssey took it further. The monoliths, silent, enigmatic, and seemingly guiding human evolution, were more than plot devices. They embodied the idea that intelligence might not reside in biological forms at all. When H.L. sings Daisy Bell as he's dismantled, we glimpse a machine's haunting bid for personhood. Now transpose that to galaxy clusters. What if their intelligence isn't housed in matter but in the gravitational symphony between black holes, or the quantum entanglement threading dark matter filaments? Clarke's monoliths might be closer to reality than we thought, not artifacts but processes, invisible rules etched into space-time itself. These narratives aren't just entertainment, they're thought experiments that shape real science. When Carl Sagan wrote Contact, he imagined a universe crisscrossed by wormholes left by ancient civilizations, a poetic metaphor for the cosmic web's filaments. Today, physicists like Michio Kaku seriously discuss whether advanced beings could manipulate spacetime like engineers shaping clay. An Annihilation, Jeff Vandermeer's surreal tale of a shimmering zone where DNA refolds itself, finds eerie parallels in astrobiological theories about extremophiles surviving interstellar radiation by rewriting their genetic code. The irony is delicious. Sci-fi authors, unshackled from peer review and grant proposals, often stumble onto truths that take decades to enter laboratories. Octavia Butler's Xenogenesis trilogy envisioned symbiotic alien species sharing consciousness across generations, a concept now explored in quantum biology labs studying how electrons tunnel through DNA. Even Doctor Who's time-warping TARDIS, bigger inside than out, finds echoes in theories about compactified dimensions in string theory. Yet for all their prescience, these stories share a sobering lesson. Cosmic life, if it exists, will defy our templates. A sentient nebula wouldn't recite Shakespeare. It might pulse in gamma rays or sculpt its thoughts in magnetic fields. The living cosmos theory doesn't promise star whales or godlike monoliths, but it does ask us to listen for rhythms in the chaos, to recognize that the universe's most profound dialogues might be whispered in the language of plasma and gravity, played out over scales too grand for human lifetimes. Perhaps that's sci-fi's greatest gift, not predicting the future, but expanding our capacity to wonder. When we stand under the stars tonight, we're not just observers, we're participants in a story still being written, one where the next chapter might reveal that life was never just a sideshow in the cosmos, but its very heartbeat. Gravitational wave astronomy could become the stethoscope that lets us listen for the cosmic heartbeat hidden within galaxy clusters. When LIGO first detected ripples in spacetime from colliding black holes, it opened a new window on the universe, one where vibrations, not light, tell the story of cosmic events. Now imagine pointing that sensitivity toward the slow-motion dances of supermassive black holes at cluster centers. These titans don't just sit silently, they orbit one another in decaying spirals, emitting gravitational waves at frequencies too low for current detectors to catch. But upcoming missions like LISA, the Laser Interferometer Space Antenna, will tune into these ultra-low-frequency murmurs. Picture 3 spacecraft forming a 1,000,000-kilometer-wide triangle, tracking distortions smaller than an atom across the vacuum. What might they hear? The rhythmic pulsing of black hole binaries separated by light years yet bound in an eternal waltz, their space-time tremors carrying clues about how clusters regulate themselves. Meanwhile, pulsar timing arrays are hunting for an even grander rhythm, the background hum of countless supermassive black holes merging across cosmic time. These networks of ultra-precise cosmic clocks, millisecond pulsars flashing with atomic clock regularity, act like a galactic-scale EKG machine. As gravitational waves stretch and compress space-time between Earth and these pulsars, they disrupt the flash's timing by microseconds. The nanograv collaboration already detected this stochastic background, but future sensitivity could reveal distinct patterns. Are there synchronized beats lurking in the noise? Could certain clusters exhibit gravitational wave signatures that betray something more than random collisions, perhaps evidence of coordinated motion or resonance? It's like listening for the difference between a chaotic crowd murmur and the structured harmonies of a choir. But gravitational waves are just one channel. The Event Horizon Telescope, famous for imaging a black hole's shadow, could also monitor how active galactic nuclei communicate across clusters. When one black hole erupts in jets, does it trigger outbursts in others through mechanisms we don't yet understand? Some theorists propose that magnetized plasma bridges between galaxies might transmit information not as radio signals, but as pressure waves in hot gas or entangled quantum states in dark matter. The Chandra X-ray Observatory has already spotted sound waves propagating through the Perseus cluster's gas literal notes in a 57-octave below middle C chord. Future X-ray telescopes with higher resolution could map whether these vibrations carry energy in organized ways, like neural impulses or vascular pulses. On the quantum frontier, lab experiments with ultra-cold atoms might simulate cosmic-scale behaviors. When chilled near absolute zero, atoms can enter Bose-Einstein condensates, a state where quantum effects manifest macroscopically. Researchers have already used these setups to mimic black hole dynamics and cosmic inflation. What if we program them to recreate galaxy cluster environments, threading the condensate with laser-induced dark matter filaments to observe how information or energy flows? Any emergent self-regulation in the lab could hint at analogous processes unfolding in the cosmos. The most radical proposal comes from SETI New Direction, not just searching for radio signals, but for technosignatures of astroengineering on galactic scales. Could a sufficiently advanced civilization manipulate cluster dynamics, perhaps nudging black holes into resonant configurations or harvesting energy from large-scale magnetic fields? While this ventures into speculation, the principle is sound. If life can emerge at planetary scales, why not develop technologies operating at cluster scales over billion-year timelines? Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will generate petabytes of data, perfect for machine learning algorithms trained to spot anomalies, unusual alignments of quasars, oddly synchronized galaxy rotations, or energy distributions that defy standard models. Critics argue this is pattern-seeking run amok, that clusters are just physics in action, no more alive than a whirlpool in a stream, but science advances by testing boundaries. The hunt for cosmic vital signs isn't about proving galaxy clusters think. It's about discovering whether the universe possesses organizational principles we've only glimpsed in biology. Every experiment, from gravitational wave detectors to quantum simulators, sharpens our tools for distinguishing randomness from rhythm. and in that delicate difference might lie the next revolution in understanding reality itself. If the cosmos isn't just a backdrop for life but a living entity itself, our approach to space exploration suddenly takes on ethical weight we've never considered. Imagine discovering that every time we send a probe through Saturn's rings, we're disrupting something akin to a planetary-scale nervous system, or that mining asteroids is the cosmic equivalent of stripping bark from a 1,000-year-old tree. The idea of cosmic conservation shifts from poetic idealism to urgent necessity. We already grapple with planetary protection protocols, ensuring our spacecraft don't contaminate Mars or Europa with Earth microbes. But if galaxy clusters function like organisms, our responsibilities might extend far beyond avoiding bacterial trespass. Consider the Great Attractor, a mysterious gravitational anomaly pulling thousands of galaxies toward it. What if it's not just a dense knot of dark matter, but a vital organ in the cosmic web structure? Our telescopes and probes could one day interfere with processes we don't yet understand, like a mosquito landing on a supercomputer's circuitry. The precedent exists in terrestrial ecology. Deep-sea mining threatens hydrothermal vent ecosystems we barely comprehend, destroying species before we even name them. At interstellar scales, the stakes multiply. A misguided attempt to harness energy from a quasar might ripple across millions of light years, disrupting gravitational equilibria that took billions of years to establish. Ethical frameworks would need radical expansion. Indigenous cosmologies have long emphasized reciprocity with natural systems, from the Maori concept of Kaishiakatanga, guardianship, to Native American seven generations thinking. Applied cosmically, this could mean moratoriums on altering galaxy clusters, gas flows, or treating rogue planets as protected entities rather than resource troves. Even passive observation carries risks. The Arecibo message and Voyager's golden records were launched with hopeful intentions, but if the universe is alive, our signals might be less like friendly greetings and more like invasive noise pollution in a celestial rainforest. The counterargument is pragmatic. Survival demands expansion. If Earth becomes uninhabitable, humanity's future may depend on spacefaring. But what if habitable exoplanets are cosmic eggs, incubating life we can't detect? The debate mirrors terrestrial conservation dilemmas. Do humans have the right to bulldoze rainforests for farmland if it ensures our survival? The difference is scale. A forest regrows in centuries. A galaxy's injury might take epochs to heal. Legal systems aren't prepared. The Outer Space Treaty of 1967 prohibits nuclear weapons in space but says nothing about disrupting dark matter filaments or draining neutron stars for fuel. Pioneers like astrophysicist Lucian Walkovich advocate for astrocology, a discipline recognizing celestial bodies as having intrinsic value beyond utility. Picture UNESCO World Heritage Sites, but for quantum flux nebulae or magnetar breeding grounds. Perhaps the most profound shift would be psychological. If we accept the universe as alive, exploration transforms from conquest to conversation. The James Webb Space Telescope wouldn't just collect data, it would listen. Missions to Europa wouldn't drill with abandon but seek consent through careful study of potential biosphere boundaries. This isn't mysticism. It's the logical extension of ecological ethics applied to a living cosmos. After all, we've learned the hard way on Earth that ignoring interconnectedness leads to catastrophe. The stars may be offering us a chance to do better this time if we're wise enough to take it. The living cosmos theory challenges us to rethink everything we thought we knew about the universe. It asks whether galaxy clusters, those colossal gatherings of hundreds of galaxies, are more than just cosmic accidents, whether they might function in ways eerily similar to living organisms. From feeding on intergalactic gas to regulating their environments through black hole heartbeats, these structures exhibit behaviors that blur the line between physics and biology. The cosmic web's filaments resemble neural networks, Dark matter's distribution mirrors biological blueprints, and even the universe's expansion might hint at a deeper, dynamic equilibrium. These aren't just poetic parallels, they're tantalizing clues that life, in some form, could be a universal phenomenon, not bound by our earthly definitions. Yet mysteries remain. If galaxy clusters are alive, how do we define their consciousness? Could a supercluster think in gravitational waves or quantum entanglement, its thoughts unfolding over billions of years? And what about the skeptics? Mainstream science rightly demands evidence beyond metaphor patterns that can't be explained by known physics alone. The debate isn't settled, but that's what makes it thrilling. Science progresses by daring to ask bold questions, even when they shake the foundations of what we think we know. So where does that leave us under a night sky that might be more than just a static tapestry of stars? If the universe is alive, then every glance upward becomes a conversation, a silent dialogue with something vast, ancient, and profoundly strange. The living cosmos theory doesn't just expand our understanding of life, it redefines our place in the cosmos. We're not just observers, we're participants in a story still being written, one where the next chapter might reveal that the universe has been watching, growing, and evolving alongside us all along. Now it's your turn. Does this idea resonate with you, or does it stretch the bounds of plausibility? Could the cosmos itself be alive in ways we're only beginning to grasp? Drop your thoughts in the comments below, and the next time you find yourself beneath the stars, take a moment to wonder, is the universe watching back? Keep looking up, stay curious, and who knows, maybe one day we'll find the answer written in the sky itself.